Today, Dr. Wenbo Wu is going to provide us with his insights about remote sensing of ocean temperatures with seismic acoustic waves. Dr. Wenbo is currently a assistant scientist, tenure track assistant scientist at the WHOI Institute of Oceanography. He obtained his bachelor's at University of Science and Technology of China, and then he obtained his PhD at the Princeton University. After 2 years of being a postdoc fellow at Caltech Seismolab, he's now at Woods Hole. Dr. Wu is standing in the cross-discipline through the seismology, the oceanic physics, and also the climate science. So let's welcome Wenbo.
Thank you for the great introduction. And today I'm going to talk about Okay, let's get started. Today I'm going to talk about using seismic waves to detect ocean temperature changes. And I put a picture here. You can see in this picture, these two whales, they just jump out from the ocean. At that moment, there was an earthquake occurring near Los Angeles. And these two whales, they might be perturbed by the earthquake seismic waves, or just be coincidence. And so here our team, we have seismologists and we have physical oceanographers. So here the Yuan Callis and Shiri and Hakan, they are physical oceanographers, and the others, we are seismologists. In this project, we are trying to do this kind of cross-disciplinary research to get the ocean temperature change monitoring. This is the outline of my talk. I will first introduce the motivation of the study and some background of acoustic ocean thermometry, and then I will introduce our new method of using seismic waves to do thermometry. And next is the applications to the Indian Ocean and Northwest Pacific. I will also talk about some opportunities using the emergent seismic observing techniques. And finally, is the conclusion. The climate change is one of the major crises we face during this century. In the climate change, the ocean plays a very key role there because for the global warming, due to the increasingly abundant greenhouse gases, the ocean absorbs almost all the excess energy. If you look at this figure, and this figure shows the heat absorbed by different components of the climate system, you can see almost all of the heat, it goes to the ocean, and the land, atmosphere, and ice, that only takes a small fraction of that. So that means the ocean really acts as a buffer of the global warming. Without this buffer, the warming would be much more rapid. So it's quite important for us to monitor the ocean warming. And the consequence of the global warming is, if you look at the right figure, almost everywhere in the ocean is warmed up, except some regions like here and here. So monitoring the ocean warming is critical for us to understand the future projection of climate change. But it's challenging. Monitoring the global ocean is challenging. This figure here shows the ocean heat content in the upper ocean above 2,000 meters and below 2,000 meters. So you can see both of them, they have uncertainties. These bands, they represent uncertainties. For the upper ocean, the uncertainty becomes smaller after 2000 because we just have increasing observation data. And for the deep ocean below 2,000 meters, the uncertainty is always large because we just lack observational data. So why this is challenging to get the ocean warming observation? It really comes from the complex ocean dynamics. So this animation, it shows the sea surface temperature modeling in 1 year. And if you look at this picture, the most prominent feature is that it's latitude dependent. If you look at the high latitudes, you can see these curved features. So these curved features, they are meanders. The meanders, they have typical dimension of 50 to 500 kilometers, and the lifetime is between 10 to 100 days. These meanders, they also generate smaller scale, mesoscale eddies. So the eddies, they have scale 10 to 200 kilometers, and they last days to months. So this we have these transient signals. If we move from high latitudes to low latitudes, like the equator, we don't have these strong meanders and eddies. However, we have other complex ocean dynamics, like the dynamic waves occurring at different space and time scales. And the ocean also feels the winter and the summer. So we have the seasonal changes. To resolve the long-term trend, the ocean warming, we must consider these transient signals. We need to resolve these transient signals. So this is the challenge. And to observe these ocean dynamic complexities, we have a bunch of observing tools. So this slide just to show some of these most powerful tools. And at the top here, we have the satellites. The satellites help us observe the sea surface temperature globally, and they also give us the sea level anomaly. So sea level anomaly can also tell us the temperature, because you can imagine that when we get the warm up ocean and the water just gets the thermal expansion, it increases the sea level. That can help us to tell the ocean temperature change. However, we know the sea level is also affected by other factors, like the mass change, for example, the ice sheet melting. So to get the temperature measurements, we need to also consider other signals in the sea level anomaly data. And another extremely important data, it comes from the Argo. So Argo is a global array composed of about 4,000 floats in the ocean. So each float, to save battery, most of the time they just stay at the depth of 2,000 meters. And every 10 days, this float just come to the surface and measure the depth profile, the top 2,000 meters of the temperature and some other variables. This is Argo, but Argo has no data below 2,000 meters. Below 2,000 meters, we have these two data sets. The first data is hydrographic data. And this map, you can see the hydrographic data is extremely sparse in space, and it's also sparse in time for each of these paths, and the reoccupation time is years or even decades. So they are sparse. And the mooring system, we have the mooring system. The mooring system can give us higher temperature resolution. It can give us like daily or even hourly minutes temperature resolution. However, in space, there's even more sparse compared to hydrographic data. So this is why for the deep ocean, we have the large uncertainties. And in physical oceanographer community, the goal is to get the observational data to resolve these ocean dynamic processes, like eddies and seasonal change, El Nino, these signals. And it's quite clear that there's no single observation tool which is able to solve all of these problems. And because they have just different they just have different resolution and coverage in time and space. As you can see in this figure here, the horizontal axis is the horizontal scale. And we also talk about the at depth. At depth, these different tools, they measure different depths of the ocean. So that turns out is even we combine all of these observational tools, we still have some gap, some data gap. And next, we are going to talk about how we use earthquakes to fill some of these gaps and to observe the ocean dynamics. So I'll just introduce the ocean observing tools. And there's another remote sensitive tool is acoustic ocean thermometry. So the principle of acoustic thermometry is quite simple. Basically, sound travels faster in warmer ocean. If you look at the right figure here, it shows us this relationship. With 1 degree temperature increase, we get about 4 to 5 meters per second sound speed in the ocean increase. So that means we can track the sound speed or travel time change of the sound to map or infer the ocean temperature changes. So this is the principle of ocean thermometry. And another great feature of ocean thermometry is the long distance transmission of sound. This long distance transmission is guaranteed by what we call waveguide effects. So if you look at this curve, so this curve y-axis is depth. The sound speed gets decreased with depth because the temperature gets colder, and then it comes back due to the higher pressure. So this profile, it forms a low velocity zone, which is a waveguide. It protects the sound from the interaction with the safe flow. That allows the sound propagate long distance with little energy lost. So this is the waveguide effects. And with the waveguide effects, a great thing of that is it's just the long distance, it averages out small scale ocean dynamics like eddies. And what we are left is the long range average temperature change, which is good for long-term, large-scale, basin-scale ocean warming observations. And the right figure here shows how we do it. So this figure, we have different repaths. If you have an acoustic source here, it just excites sound waves traveling with different repaths. If you have the repeating transmission of these sounds, and by looking at the travel time changes of different waves with different repaths, we can map out the ocean temperature change. So this is the acoustic tomography. The idea proposed in 1980s, and the implementation of this idea, it happened in 1990s. There are a few experiments about ocean acoustic thermometry. So this one is one of the most famous experiments. It's called ATOG. So what ATOG group did is they put 2 giant acoustic sources like this in the Pacific. So one is at Kauai, the other one at Pioneer. And these 2 sources just send out repeating sounds in the ocean. And they just track the travel time changes. The travel time changes observed at these hydrophones. And the right figure here, it shows the observed, this is travel time change or travel time anomaly. And on this side is the temperature. And you can see the amplitude here is 0.1 degree. So the blue dots, they are observed temperature changes. And finally, they got the ocean temperature change monitoring with an accuracy about a few millidegree. So this experiment, the duration was 10 years. They spent only $20 million to achieve this great scientific goal. So this is a very good example of using limited resource to achieve this scientific goal. It's very successful in that regard. However, ATOG stopped in 2006 because they got troubled about the potential impact on marine mammals. During that experiment, there are lots of media reports and public concern about the potential of this active source because they might disorient or even kill whales. ATOG group, they did some studies about this, and the conclusion is there is no significant impact on marine mammals, but it did raise the permitting issue for these experiments. The right figure here shows us different acoustic sources in the ocean. You can see there are all kinds of acoustic sources. We're ready to think about how to better manage these acoustic sources in the ocean, just for the health of the ocean ecosystem. If we are not allowed to use active source to do ocean thermometry, do we have other choices? And so this figure shows all kinds of acoustic sources in the ocean. And the green color is from marine animals. In the past decades, the community just tried different kinds of acoustic sources to do ocean thermometry. But none of them is successful at a basin scale. One reason is that these sources are just too weak to propagate basin scale, thousands of kilometers. Even we have the waveguide effects. If you look at this figure, the y-axis represents the power of these sources, and the earthquake sits at the top. So earthquake is the most powerful acoustic source and in the Earth. So does earthquake work for ocean seismometry? And next, we are going to talk about how we overcome some difficulties to make earthquake work for ocean seismometry. This is one example of how earthquakes generate acoustic waves in the ocean. So if you look at this figure, suppose we have an earthquake here in the crust. It generates seismic waves, P and S wave, primary and secondary wave, propagating upward to the seafloor. And these seismic waves just converted at the seafloor, converted to acoustic waves, and then propagated in the SOFA channel. Finally, this sounds or acoustic waves, they are recorded by hydrophone or seismometer. This one, DGAR, installed on a small island. And at the bottom is real observed data from earthquake here. It's about 3,000 kilometers away. And you can see in this seismogram, we have this primary P wave at this frequency band. And S wave is barely visible because it gets attenuated in the solid Earth. And after about half hour after the earthquake occurrence, you can see there's a very big signal. This signal is the sound wave generated by the earthquake. It arrives after P and S wave, so it's called tertiary wave, and T wave or T wave. T wave is readily observed at 1 to 10 hertz. So this is what we are going to use in ocean seismometry. Also, earthquakes in the ocean, they generate very strong acoustic waves, but not all of them, they are useful for our purpose. The reason is that the T wave is quite complex. I mean, by that, I mean the propagation in the solid Earth, because we know the solid Earth the structure is complex, right? And in addition, we don't know exact location of these earthquakes. So that means we cannot use absolute travel time to do the ocean seismometry. And for this problem, we just we solve this problem using repeating earthquakes. So repeating earthquakes means if you look at this figure, we have earthquake A occurring a few years ago, let's say, and then we have this earthquake B occurring at almost the same location, but different dates. They are repeating earthquakes. Because they are at the same location and their waveforms, T wave waveforms would be very similar to each other. So this is what we are using. We are using acoustic waves from repeating earthquakes. The same idea as ATOG, but the source is replaced. The active source is replaced by natural events. The T wave data here we are using is recorded by CDBDO hydrophones and T-phase seismometers. Seismometers means they are installed on land. So on the right figure here, you can see this is the CDBDO hydrophone. CDBDO stands for Comprehensive Nuclear Test Ban Treaty Organization. They just built up a global network to monitor the nuclear explosions. For us, we just use this data freely for ocean monitoring. And you can see this giant float. This float helps the hydrophone float in the ocean, in the SOFA channel, to record the acoustic waves in the SOFA channel. So this is the data we are using. And let's look at one example of repeating earthquake data. So this is one repeating earthquake pair. And the first event happened in 2006, the second one in 2008. So the left map here shows the repeating earthquakes. So each star is one repeating earthquake, and I believe this pair is it's one event located somewhere here. And this zoom out map this is our source region, Sumatra subduction zone, and we have this big earthquake, 2005 magnitude 8.6 earthquake. And the T wave we are looking at is this one, DGAR seismometer. And on the right, the top figure shows the P and S wave recorded by local seismometer, PSI here. You can see their waveforms are very similar to each other. And there is also a hidden seismogram here. So this hidden seismogram, you can see it does not match with the blue line because this is due to the origin time error. And what we can do is to shift the seismograms to make them match each other. That help us synchronize the repeating earthquakes. And after synchronization, if you look at the bottom figure, this is the T wave recorded by DJAR. The waveforms are also similar to each other. But this is the travel time change. And this travel time change, negative 0.27 seconds. Negative change means the ocean in 2008 is warmer than 2006. So this is from this one example. We got the travel time change, but what we really want is the ocean temperature change, right? So that means we need to solve another technical issue. So this issue is relating travel time change to temperature change. And here what we do is we are using the numerical tool spectral element method spectrum 2D to solve the wave propagation problem and to calculate the adjoint simulation results and get the sensitivity kernels. So spectrum 2D is widely used in seismology, and we just use its two-dimensional version because the 3D simulation is very expensive. And for the model using spectrum 2D, here we use echo to construct the 2D sine speed profile along our T wave path. So just briefly what echo is. So echo is kind of data assimilation ocean model. And the echo group just combines all the observational data, including satellites, Argo, hydrographic data, as well as ocean physics modeling. So there's physics modeling in echo. And we just extract their temperature and salinity data to construct our sine speed profile, and then run spectrum 2D simulations. So we are going to talk about echo a lot in the following. And this figure, it gives us the simulated results in sensitivity kernels. And you can see, as we expect, the high sensitivity kernels, they are concentrated in the ocean SOFA channel, and they get muted at the top and bottom ocean. And you can also see there are some oscillations, right? Here, there's oscillations. These oscillations are due to the shallow bathymetry features here. They generate the scattering waves. If we calculate the sensitivity kernels below 2,000 meters, it's about 40% sensitivity kernels below that depth. That means our data well complements Argo data. And then let's look at this specific repeating earthquake pair we talked about in the previous slide. So the middle figure here shows the echo temperature change along our T wave path. And you can see at the top, there's very strong temperature change, which makes sense. However, T wave is not sensitive to that because the sensitivity kernels, they look like this. What T wave really feel is just the product of sensitivity kernels and the ocean temperature change, which is plotted in the right figure here. So this is what T wave with the measurement we can get. And you can see there's a big blob here, red. Red means temperature increases. And if we add up contribution from each point of this 2D profile and get the integral, finally we get this number. The predicted travel time change is negative 0.14 seconds. It goes the same sign as the observation, but the number is underestimated. And here I want to note that this distribution is for spatial distribution, is from echo. For our data, we don't know this distribution. The only thing we know is the integral effect, the total effect. However, previously we talked about using one frequency band result. If we using multiple frequencies and measure the travel time change, that can give us the depth distribution, the depth spatial distribution of the temperature change. And if you look at this figure, this is the kernels for different frequencies. We have 3 frequencies here. The low frequency samples deeper ocean. And if we use these 3 frequencies, we can resolve the depth distribution. This is the same idea as surface wave tomography in seismology. And so what we can do with these 3 frequency measurements is we can just decompose them with the singular vectors. And the middle figure here, it shows us the first 2 singular vectors. We are going to use these singular vectors to do depth tomography. This is the third singular vector. We just don't use it because the third one has larger uncertainties. The reason is if you look at this in the kernels, they're pretty similar to each other. That means the third one uncertainty is large. And the right figure here shows our resolution. And you can see the resolution is not good. It's not better than 1 kilometer. However, even with low resolution, it's still valuable for us to look at the ocean temperature change. And we can also do horizontal tomography. For example, in this published paper, what we do is this is Japan, and we have the repeating earthquakes, red stars. What we do is we got the data observed at this hydrophone H11, and we divide this data using their azimuths from north to south. So we have a number of azimuths. For each of these azimuths, we measure the data, we do the inversion and get the temperature change. So this is the horizontal resolution. So I talked about the observations, the measurements, different frequencies, different azimuths. And then with these measurements, the problem, it becomes an inversion problem, linear inversion problem. So this equation, it describes what the problem in hand. We have the observational data, trial time change, and A is the unknown parameters we want to get, we want to solve. It's a time series of the ocean temperature change. And E is the design matrix. We have the noise, the data have the noise, right, described by N. And then we just use the Gauss-Markov estimator to get the time series estimation as well as uncertainties. There are lots of technical details in the inversion, which I don't want to talk about. But this is one thing I really want to talk about is the covariance matrix R and the noise matrix N. You know, typically when we do the inversion, the Bayes inversion, what we can do is we just specify the parameters of the covariance matrix, right? Using our knowledge, for example, using our physical oceanography knowledge. But here, what we do is we want to let the T-wave data itself to tell us these hyperparameters. And what we can do is just using the type 2 maximum likelihood method to estimate these parameters. And the top figure here just shows one of these hyperparameters. This parameter is the space correlation scale for the ocean random dynamics. And the results we got here is 60 days. 60 days, this is consistent with the lifetime of ocean eddies. So that tells us the data here, and you can use just pre-specified parameters. But if we use T-wave data itself, give us a very similar, reasonable answer for that, which is great. So we're talking about the technical things. And next, let's look at the most exciting part, the final results. So this slide shows the results we got 4 years ago. And in this study, what we did is, again, this is Sumatra. We use this about 2,000 repeating earthquake pairs coming from about 900 earthquakes. We were a little bit surprised by so many repeating earthquakes. And I think part of the reason is the waveguide effect. It really helps to increase the signal noise ratio. And many of these earthquakes, they are below magnitude 4. So even magnitude like 3.7, we can get the signal at 3,000 kilometers away, which is amazing. And in the right figure here is we are using these 2,000 repeating pairs to do the inversion and get the time series of the ocean temperature change. So here, this is ocean temperature anomaly, positive goes up. And we just plot 3 results here. Our T-wave result, Argo, the prediction by Argo climatology, and Echo. So the prediction is the same way as we talked about for the previous repeating earthquake example. And if you look at this figure, generally, they are consistent with each other, right? But if you look at the details, for example, these signals, they are seasonal changes. Both Echo and Argo, they more or less underestimate these seasonal changes because they're limited resolution. And if we look at the linear trend, the long-term trend for this part of the region, this T wave path, and we got about 4.4 millicurrent per year ocean warming, positive ocean warming. It's a bit stronger than Argo and Echo results. If you zoom in here, you can see we have lots of repeating earthquakes. The reason is in 2005, we have the big earthquake. That big earthquake just triggered lots of aftershocks. So that means it allows us to zoom in this time window to look at the small scale temporal resolution of the time series. And here we have about 1.5 months time series. And you can see Argo, the orange curve is quite flat because it has 10 days resolution. And if you look at our results and Echo, you can see these signals, right? These bumps. And these bumps, they are associated with ocean dynamic waves. And here I want to draw your attention to this big bump. This big bump, the duration is about 2 weeks. So what this signal is? It turns out this signal is the ocean equatorial waves, specifically Yana waves. So this is equatorial waves because it only appears on the equator. The reason is when these waves deviate from the equator, the Coriolis force would push it back to the equator. So it's trapped on the equator. And this figure shows the temperature perturbation due to this, due to the Yana waves. You can see it's an antisymmetric pattern of this temperature perturbation. And on the right figure here, it plots us the results of the power spectral density of our T wave results and the results from these two model results, Echo and Orpheus. So both of them, they have the ocean dynamic simulations in their data. However, they used different boundary conditions and model parameterizations, so their results would be different. And on the right figure, if we look at here, so this is we just zoom in this zoom in this frequency range and plot it on the right here, and you can see both Echo and Orpheus, they underestimate the amplitude of the Yana waves. This is the comparison between our T wave results and these two modeling. We have independent results to support this this conclusion. So here what we plot is we have 3 mooring sites. Japan installed the mooring systems in these 3 years at these 3 sites on the equator. They measured the ocean current meters, and what we can do is get the ocean current meters, do the same thing, do the spectral analysis, and to plot the power spectral density. They are plotted on the right figure here. So this one is for Orpheus, and this one is for Echo. I would draw your attention to the solid lines because the solid lines here is their modeling results sampled at the mooring depths. And you can see both of them, the amplitude, they are lower than the mooring observational data, consistent with our results. So these results, they are important from ocean, physical ocean perspective, because if we want to get better modeling, we need to know what kind of boundary conditions and what kind of model parameterization we should use. And the observational data just help us to validate or guide us to see which one is better. And we look at the Yana waves, equatorial waves observed on the equator path, this T wave path. Now let's switch to another T wave path. So this path is, it samples more higher latitudes ocean, and it's recorded by WHOI, this hydroform. And on the right figure here at the top, again, we plot the time series for the these 3 results. And we have the seasonal changes. But if you look at that in detail, you can see these spikes, right? Like these 3 triangles marked here. These spikes, turns out they are due to ocean eddies. And we have independent data to support that. At the bottom here, what I'm showing you is the sea level anomaly distribution. And you can see on our T wave path for these 3 days, each of them, they're hotspots, these hotspots on our T wave path. And the hotspot here, they are higher temperature due to the ocean eddies, typical dimension 200 kilometers. And these signals, they are captured by our T-wave results, another kind of transient signal at high latitudes. So we look at these two types of transient signals on the equator and high latitudes. They show difference. Let's look at the long-term trend. And this figure shows the long-term trend for these two T-wave paths. So the right figure is the constructed depth distribution of the ocean temperature in this 13 years. Red is warm, blue is cold. And if you look at the top, it goes from blue to red, warmed up. But here I want you focus on the deep ocean. The deep ocean here means, for example, below 2,000 meters. And for the deep ocean, there's a difference. For the Diego-Garcia pass here, the deep ocean is not warmed up. It becomes colder. And I put a number here. So this number is it's the amplitude of the second singular vector, tells us more the very deep ocean temperature change. It's negative. And for Cape Leuven pass, it's positive. It's warmed up. There's a difference between them. And the next one we have worked out is this hydrophone. It samples the Kuroshio region. So this is Japan, and it samples, as you can see here, we have very complex ocean dynamics here, represented by this meander. And what we do in this case is do the azimuth tomography, because it's the result is the ocean dynamics is so complex. We would see for different azimuths, the temperature change, the time series would be different. And it's shown on the right here. So on the right here, at the top is our T-wave results. Y-axis is different azimuths. We have different years. And the bottom is from the satellite sea level anomaly results. And you can see the general patterns, they are consistent with each other, especially for the years after 2011, the big Tohoku earthquake, right? And if you look at the azimuths, go from north to south, and there's azimuth difference. For this part, it's warm, and for the positive azimuth, the north part, it's cold. We're talking about the applications in these two parts of ocean, and we demonstrate that the seismic data, it helps us to beat down the uncertainties, but how much it is. And here in this study, what we do is we do the inversion for using different data sets. And we have 3 lines here. The orange and green curves, they are inversion using data separately, using seismic data and using the conventional data. Conventional data including Argo and shipboard CTD data. And the blue curve is combining them together. And the bottom plotting here is the uncertainties. And you can see after 2011, if we're using seismic data for this specific region, the seismic inversion result, the uncertainty is smaller than that using conventional data. Before that, we have larger uncertainty because earthquakes are limited. However, if we combine them together, we can always get better results in terms of smaller amplitudes. And if we look at the linear trend of this time series, and which is plotted on the right here, you can see the warming trend for this specific region, the ocean, is between 6 to like 12 millikelvin per year. This region is the trend is even stronger than the Indian Ocean, the really warmed up region. So just a summary here. We have the ocean dynamics complexities there, and we need different tools to resolve them. And we demonstrate the SOT, seismic ocean thermometry. It does help us to fill some of these gaps. And we observe the transient ocean dynamics, the eddies, which belongs to this barotropic variability. And we also, the eddies is located here, and we observe the Yana waves, which belongs to the barotropic variability. And we also got the long-term, large scale ocean temperature change located here. And it really complements the traditional data, especially for depths below 2,000 meters, as reflected in the sensitivity kernels. So we have worked out the three hydrophones. The three hydrophones, and in this map, there's three hydrophones. We have more hydrophones, right? This is what we are working on now. And globally, CDBO have like between 10 to 20 hydrophones, which we are working on now. But what's next? What's the next plan? Because globally, even with these hydrophones, the data is still very limited. And we just asked the CDBO, is there any way to expand this global network? CDBO said, well, that's kind of unlikely, because if you want to increase any hydrophone, you need to get the agreement between all the countries of the CDBO. That sometimes very challenging, right? Especially currently. Well, and for us, is we need to sort out other solutions costly efficient and logistically easy way to do that. And turns out we do have the opportunities. The opportunities here that I'm talking about, the first one is the emerging technique of distributed acoustic sensing. This is a kind of hot topic in seismology in the last few years. What this technology does is it turns a tens of kilometers fiber optical cable into thousands of seismometers. And how to get that is what we do. We can just attach an interrogator to one end of the fiber, shoot out the laser into the cable, and by observing the scattering waves of these light signals, which are affected by the ground vibration, we can turn the cable into a seismic array. So this is the idea of distributed acoustic sensing. This technique has great potential advantages, but there are also challenges there. One of the biggest challenges is the data is very noisy. So in this study, my postdoc Zhe Jia, what he did is we developed a curved-based denoising method to increase the signal-to-noise ratio. And we applied this method to these two cables, WHOI cables, offshore Oregon. And it turns out if we are using the raw data without denoising, we can detect T wave from earthquakes at Aleutian with magnitude above 4. So this one, the green star. If we do the denoising, we can lower the magnitude to 3.5. That helps us to increase the data a lot. For comparison, if we are using the ocean bottom seismometer and the magnitude threshold is 3.7, so thus the performance is a little bit better than single ocean bottom seismometer. So that could give us more data for the ocean, but there's a limitation there. Another limitation for DAS is with the current technique, we can only use tens of kilometers cable near the coast. That means we cannot get the data in the open ocean. And here, another emerging technique, in my view, which is game-changing, it's the float hydrophones. So the float hydrophones is the same idea as Argo. Here, we just put the sensor, the hydrophone sensor, in the float like this, and let them drift in the ocean. The group led by Frederick Simons at Princeton University, the Earth Scope Oceans, they have deployed tens of these float hydrophones in the global ocean. Most of them, they are located in the Pacific Ocean, this part. And you can see on the left here, we have the seismogram. You can see very clearly T wave observed from this earthquake about more than 3,000 kilometers away. So here we really want to know, if we get an Argo-like global array, can we get a high resolution, real global 4D ocean temperature tomography? And in this study, we did the synthetic test. So what we do is we have this kind of Argo distributed. Oh, sorry, the resolution is low, but it's fine. We have this Argo array. And on the right figure here, it shows if we suppose we have the float hydrophone uncertainty about 100 meters, which is currently we believe using our locating method, we can get that kind of location area of the hydrophone. With this area, and if we look at the uncertainty here, the green curve is using Argo data alone. And if we add up our seismic data, and we can beat down the uncertainty by about 20%. So this is domain averaged estimate. And the bottom figure here is point-wise for specific location. And in that case, we know seismic waves, they are integral effects, right? They tell us the integral effects. But even with that, for point-wise estimate, we can still beat down the uncertainty a little bit. And using this technique, one thing I forgot to see is that the way to use T-wave is different. Here, we are not using repeating earthquakes. We are using the same earthquake, but T-waves recorded at 2 different stations. And we are measuring the relative trial time between the 2 stations. In that way, we are not limited by repeating earthquakes. Every earthquake above like magnitude 4, we can use them for SOT. This plan it aligns with the dream of global seismology. If you look at the global stations distribution, the ocean is really a gap, and we really want to fill this gap. So in the future, we really hope this dream can be realized. And if just doing one applications, for example, like Frederick Simons, and they using the mermaid floats to do deep Earth imaging, mantle imaging, and that would be not very easy to convince the funding agency, right? Because it's the cost. We need to think about the cost. However, if we can maximize their scientific returns by combining all these applications, deep imaging, deep Earth imaging, SOT, seismic ocean thermometry, natural hazard mitigation, and that would make it easier, and we get a stronger support from these agencies. And hopefully in the future, we can get that. This is the conclusions. And SOT, we get the data complementing their conventional measurements, and in the future, and we hope SOT can become a critical data source for assimilating ocean state models. Thank you.
Thank you, Wenbo. Great talk. First, we would like to invite questions from students. I'm not sure how many students are here.
Can we take the microphone? I should take this. Oh, thank you. So yeah, this is the microphone. Yeah, amazing. So thank you for your great presentation. And I have a question about from your introduction, I think the T wave is quite similar to a surface wave traveling in the ocean. Yeah, and it's like I think it's like depth sensitive kernel is somehow like a surface wave. So I wonder whether the T wave can also be recovered from something like ambient noise interferometry between 2 stations. Yeah, so I think if it can be recovered from noise interferometry, then probably we can have higher temporal resolution, because the repeated earthquake is it's not happening at any time everywhere also. Yeah.
Thanks for the question. Yeah, the answer is yes. And actually, Georgia Tech, the group, they have done this work like 10 years ago. What they did is they used the CDBD hydrophones with distance about 100 kilometers away from each other, do the ambient noise cross correlation, and they did get the signal, and they map out the ocean temperature change. They get very nice results. But the issue there is we can get the results about 100 kilometers. If we increase the distance to thousands of kilometers, and then we cannot see the signal. The reason is the longer distance, right? You need a longer length of data to get the convergent signals. And turns out with like a month or year data, it's not enough. And when this length becomes longer, practically, well, it's not It's still useful, but it's we need to wait for like another 10 years or decades to get the data.
Thank you for your answer.
Other questions?
Thanks, Wenbo. Nice presentation. Great to see you again. So at the end, you mentioned that maybe you can get out of the constraint that you need repeating earthquake. You can probably get the T wave, T phase from two stations from the same earthquake. But then you need to require that ray path to be similar in that case. So just to make sure you're sensing the same slice of the ocean, I guess. So you want to find stations that on the same ray path, something like that?
Yes, that's right. You get the point. And very important reason for that is we want the azimuths very similar to each other. If they have different azimuths, one challenge there is their T waves would be different,
Okay.
right? And we just cannot measure the trial time change. The waveforms are different.
So then in that case, you need to carefully select the station you can use because you
That's
allow
right.
some like change in the azimuths because they can't be exactly the same. But
Yeah. And then the question is how much the separation, the azimuth separation we need to get the good measurements. Now we are collaborating with the Princeton University to get the real observational data and see how that performs, what kind of azimuth difference we should choose for the measurements.
okay, so I guess you're doing some forward modeling to see how, the cross correlation between two T phases recorded by different stations, then how much you can allow that.
Yeah, that's right. And this, I would say, we can only know this by the observational data. We can do some simulations, but we have the mermaid floats
Yeah.
there.
Mhm.
And Patrick said these mermaid floats, they're going to die like in 1 year. We just ask the time to request the data.
Yeah, okay, thanks.
Hi, Wenbo. Thank you for a great talk. I thought that was really interesting. My question is maybe a bit long, but hopefully I'll be able to get to the point. You showed like the one slide in particular with DAS about sensitivity to kind of earthquake magnitude for a particular case. But in a broader sense, I wonder if you could talk about, kind of what size earthquakes you really need to be able to do this. In some of your maps, you showed kind of global, oceanic repeating earthquake distribution. A lot of those are on mid-ocean ridges. Are those earthquakes big enough to create like a substantial T wave that you can pick up like with your methodology, or are you kind of restricted to subduction zone systems? And then I guess related to that, if you could just comment on how that kind of limits the oceanic systems that you can observe, or kind of those sorts of constraints are what I'm interested in. Thanks.
Thank you. Yeah, I got a lot of good questions today. Yeah, so the question is for the size of earthquakes and the earthquakes in different tectonic settings. So for the size of the earthquake, it depends on where the earthquakes are. For a few reasons. One reason for that is if so in these slides, they're talking about the earthquakes as subduction zones. And for the mid-ocean ridges, does it work for mid-ocean ridges? It becomes a little bit complicated. The first one is these mid-ocean ridge earthquakes, we know they are not very efficient to generate T waves because there we don't have the shallow bathymetry within the sulfide channel. And another question related to that is there's a proposed hypothesis that for mid-ocean ridge earthquakes, the T waves, we observe the T waves, but these T waves, they may be generated by the sea surface roughness or internal waves. If this is the case, we cannot use them for SOT using repeating earthquakes because the sea state every second, every minute, they are different. We just cannot use them. And in this published paper, we just do some analysis using numerical simulations, observational data. We prove that for mid-ocean ridge earthquakes at a low frequency, at least for low frequency below like 5 Hertz, they are generated by the seafloor bathymetry variation. They're scattering there, and then we can use them for SOT. However, the magnitude must be larger because they are not efficient to generate T waves. I would say for subductions, if there's no bathymetry blockage and the T wave path, like a magnitude 3.67, that would be very great for SOT.
Thank you so much.
Yeah, great talk, Wenbo. And I would like to know, except for the T wave, is there any other physics we can use to do the similar things to perform the SOT?
Yeah, the answer is yes. And now we are using shorty waves. I guess here is lots of people very familiar with the shorty waves, right? If I'm working on marine seismology. And we know the shorty waves, they have the scientific kernels concentrated in the bottom of the ocean. This is really great because this is really what we want. And now we are using the shorty waves from repeating earthquakes to look at the abyssal ocean warming. This is another kind of wave we are using.
Cool, great. Jamie?
How are you managing the data? Nice. How are you managing the data? I mean, you know, you've got hundreds of aftershocks from a big earthquake. How are you discriminating? How are you deciding what data to use? Are there data you use or don't use?
Oh, yeah.
And
Okay, yeah, I think I forgot to talk about that. So in one slide, I showed the P and S wave results recorded by the local station, right? And in that slide, we can see the P and S wave, they are very similar to each other. And in seismology, we have existing method to identify which earthquakes they are repeating earthquakes. And the criteria is when their waveforms are similar to each other sufficiently, we identify they are repeating earthquakes. There is some debate about that. For example, using cross-correlation coefficient, what kind of threshold you choose for that? It's 0.8, 0.9, this is the issue. But here I want to point out is it's not a problem for us because even the cross-correlation coefficient is low. That means two earthquakes, they have larger distance separation, but we have the uncertainty estimate for that. The larger distance separation, and we just put larger uncertainty for these measurements. And this is what we do in inversion, right? Once we have a good quantification of the uncertainty, we can just put that even better data in the inversion.
We got a question from online. Right? I think.
Yeah.
Patrick.
Hello. Yes. Can you hear me? Yeah. So yeah, very nice work. Very exciting. I have two questions, if you don't mind. One is there merit to have seismic receivers at the seafloor, and how sensitive would those be to thermal changes? And that was one question. The second question is regarding your joint inversion for the seismic waves, and then using also hydrography, where you showed trends from the separate estimates and then from the combined estimates. And yes, exactly this slide. What I was wondering, the area mean has the combined trend larger than either the pure seismic or the what you call conventional. Is that readily explainable? One would have thought that maybe some sort of weighted average of the trends of the separate ones, but here the combined one is larger than either of the two.
Okay. For the first question, I think the first question, if I understand correctly, is the T wave data, right, at the ocean bottom seismometer for that one.
Yeah.
Okay. Yeah, for that one is we did observe T wave at the seafloor, at the ocean bottom seismometer. And for this signal, because the T wave is trapped in the ocean sulfur channel, right? And
yes,
the symmetry kernels, we look at symmetry kernels, we do have some symmetry kernels at the seafloor, especially for low frequency T wave, because their eigenfunction is wider. So that's why we see the signals on ocean bottom seismometer. But the signal noise ratio is much higher than the receiver in the surface channel. I think one reason is T wave amplitude is smaller, and the other reason is noise is higher. The ocean bottom we know, right? The ocean bottom is always noise. So it's not, that's, I would say that's not good for SOT studies. We have not tried that yet. And
Okay.
the reason is OBS only, typically we have 1 year or 2 year data. It's kind of not very useful for SOT. And second question, I didn't think about that deeply. And so is there interpretation for that? I would say here it becomes a little bit complex. We really need to think about that because here is it's an inversion. And in the inversion, we have this covariance matrix, right? And we put 2 different data sets into this inversion. The question is, and finally, the results. Is it just we'll get some results between these 2 data sets, or we'll get the warming trend higher than either of this data set? Maybe we would get a warming trend higher than either of this one. Yeah, I didn't think about that in deep.
Okay. Well, thank you. Thank you. Great work. Thank you.
Okay, I may have one last question regarding the kernel. You use 2D profile to calculate the kernel. I'm wondering how the potential 3D structure will impact the kernel calculation, and also other factors in the ocean, such like the ocean flow and the salinity variations can also pose a challenge.
Yeah, maybe I think I can answer the easier one, the second question. So for the second question, is the answer is the salinity and current, they do affect the arrival times, but it turns out we did some, we use echo to calculate the effects, and turns out their effects are order of magnitude weaker than the temperature effect. So we, in our result, we just ignore the current and temperature effects, yeah, as it shows in this figure. Oh, sorry, it's not this one. Oh yeah, it's this one. And you can see the green curve is the temperature effect, and the blue and orange, they're much smaller than temperature effect. And your first question is about salinity kernels. That one is a tough one. To that question, I would say if the ocean dynamics is not that complex, like a coral shell region, and 2D simulation would be enough for us, because laterally, even we have wider 3D salinity kernels, right? But this part of the ocean, they have similar temperature change, and then it's fine for us. But if the lateral change is complex in terms of ocean dynamics, we need to think about in 3D case, how the salinity kernels, they look like, both laterally as well as in depth. And in that case, we need 3D simulations. We have not done that yet. And I think in the future, we are going to work on that. Hopefully.
That's going to be computationally very costly.
Yeah. Now we just cannot do it because it's 1 Hertz simulation, thousands of kilometers. Very expensive. Even with 2D simulation, we need hundreds of CPU cores to run like 10 hours to get the result. That's 2D simulation.
Thank you. Okay, if there's no question, let's thank Wenbo again.